Okay, so we're on there showing screen. So I'm going to talk to you about artificial cognitive systems and about the course that I'll be giving. So the first thing to notice is that there's a lot of topics that we're going to cover. We're going to start off looking at the nature of cognition. We're going to look at the paradigms of cognitive science. Then we're going to look at cognitive architectures. We're going to look at autonomy, embodiment, learning and development, memory, prospection. We're going to look at knowledge and representation. We're going to look at social cognition. And you'll see that, well, that's a lot of boxes. So part of the course is to make sure that this doesn't happen, that we overload you with too much information in a way that you can't handle. So in the next 18, 19 minutes or so, what I want to do is I want to go through each of these topics and explain what's involved, so to give you an idea of what we're going to be doing. So this is the kind of robot that I'd like to build and that a lot of people would like in their house. And we don't have them today, and the question is why? So we're familiar with robots which come from industry, which work in factories. And the point is that these robots work in controlled environments. We know what to expect. We can program the robot to do what we want. And what we really want are robots that can work in a complex environment where we don't know what to expect. Anything can happen, and the robot has to be flexible and has to be adaptable. Of course, it doesn't just work inside the home, it works outside for applications in search and rescue as well. So unpredictability and flexibility are what we want to be able to handle with our systems. So the idea is that we would like to build systems which can look at a situation like seeing a dirty shirt and saying, aha, okay, in order to fix this, I need to wash it, I need to know what temperature to use, and then when it's washed, I need to hang it up and dry it and possibly iron it. So a cognitive system then is a system which is autonomous, which can perceive its environment, which can learn from experience, it can anticipate what's going to happen, it can predict, and then it can engage in some action, it can pursue a goal, achieve some outcome, and if circumstances change, it can adapt to that. And the key issue here is that we want them to be autonomous. They need to work on their own, ideally without input from a human being. Another way of putting this is that it's a system that constantly predicts the need for action. So it's constantly trying to figure out, well, what could come next and prepare to act and then engage in some effective action. So when you think about cognition and cognitive systems, you think about predicting the future, breaking free of our perceptual system, breaking free of the constraints of our visual system, imagining what could happen, and then preparing to act accordingly. So cognition is prospective. That's one of the key messages from today's webinar. The second key message is that we would like to build software systems which don't have to be pre-programmed with all the knowledge they need in order to operate. We would like to build systems that can develop, that can learn for themselves. So we don't want to have to always pre-program and put all of the information required to make them work into them before they get started. So moving on to the second topic then that we'll cover in the course, the paradigms of cognitive science. One of the issues is that it's got a very, very long history. It all started with, in fact, cybernetics and Norbert Wiener in the early 40s and Ross Ashby. But it's also got roots in cognitivism, which is in fact where artificial intelligence started in the DARPA workshop in 1956. But there are other strands to it as well, in active systems in the 70s, and then a lot of formal work that was done in neural networks and synergetics and dynamical systems theory, which was very influential early on and is still today. And what we will do in this course is I will show you where those roots came from and how they have produced today the different brands of cognitive systems we have, from the AI systems in cognitive systems all the way through to emergent systems, including dynamical systems and neural networks. Now, there's a lot of different ways that you can compare the two, what we call paradigms, the cognitivist and the emergent. I'm not going to talk about them here, but we will do in the course itself. So there's at least 14 that we can talk about. So moving on to cognitive architectures, this is the third topic in the course. This is a very pragmatic issue. The idea is to figure out how you can design a software system in order to achieve some kind of cognitive capability. So we're going to look at the essential modules, the relationships between those, and then the algorithmic and representational details in each module. Now, one of the things I want to pick out here as I go through the talk is try to flag where you will be learning some of the inputs for these topics. So in algorithms and data structures, we'll cover some of the issues you need. In the same way, we'll do the same in AI, and we'll do the same in machine learning and in computer vision. So in a sense, this course here, Artificial Cognitive Systems, is a way of collecting a lot of what you'll be learning in the other courses. Cognitive architectures have many desirable characteristics. We'll walk through those. Perception, you'll learn about that in computer vision. Reasoning, you're going to learn about that in AI. And I'm going to try and pull all this together for you in this course. And it's worth noting that cognitive architecture is a term which originally had its roots in cognitivism, or AI, and has been borrowed by the others, and they've adapted it to their own purposes. And we'll talk about how they've adapted it. This is the slide that I'll be talking about in my course, which will help you explain that. The key thing here is the idea of representational formalisms and algorithmic formalisms. Again, something I'm going to cover in the first semester in algorithms and data structures. And down here on the right and left-hand side, we'll talk about knowledge, and you'll cover that in AI. So the point here is that there are differences between how you approach the building of cognitive systems, depending on whether you're on the left-hand side or the right side. I'm going to take you through a couple of example architectures. Here are some famous ones in the cognitivist side. The same in hybrid. We'll walk through a few of those and explain them, and also over on the emergent side. This is a typical picture of how SOAR, one of the most famous cognitive architectures, look like. The key thing is, you're looking at this, you'll see that memory plays a great part in this. And I'm going to say more about memory, both here in the webinar and later on in the course next year. I'm going to talk a little bit as well about humanoid robotics, because that's one of the areas of application of cognitive systems. And this is a robot that I was involved in designing. So I'll tell you a little bit about it. It's called the iCub. It's a small childlike humanoid. It can crawl. It's currently being developed so that it can walk. And it's got hands that are articulated, 53 degrees of freedom, which means 53 motors that it has to control. And so you can see the hands can move quite flexibly. Currently there are 29 of these in the world today, but the people I work with, they want to go a lot further than that. We hope that we're going to have at least 100 in the next 10 years distributed around the world. For the purposes of the course, I'll be talking about the iCub cognitive architecture, and the key thing here is that it was built on psychology and neuroscience. So it's computer science, psychology, and neuroscience blended together to build a system. This is just a box diagram of the various components. Exogenous salience, you learn about that in computer vision. This shows you here a hand moving in the background, and a thing called optical flow, something you'll learn about. This is a way of manipulating an image. This is called a log polar mapping. Again, that's something that we'll talk about in this course. I'll show you an example. And visual attention, where should I look if I want to find things that are interesting? I'm going to talk about memory in a moment, because memory is pivotal to any artificial intelligence system. And here is an example of where graph theory, which we'll be covering in algorithms and data structure, where that's important in implementing memory systems. This is called a procedural memory. That's a memory of skills, how you do things. And we'll talk a little bit about neural networks as well. Again, something that's covered in artificial intelligence. This is called a spiking neural network rather than a continuous one. And then finally, a winner-take-all competition to decide what to do next. That's action selection. Okay, so that's the cognitive architectures. Now we move on, having covered the general areas of the nature of cognition, the paradigms of cognitive science, and cognitive architectures. We'll now get in a little bit deeper into various issues. The first one will be autonomy. And here we've got a problem. Autonomy turns out to be very, very difficult to define, either in words or in mathematics. And part of this course is going to be devoted to effectively navigating this maze. But we'll distinguish between autonomy from a robotic point of view and autonomy from a biological point of view. In the robotic point of view, I'm going to split it up into 4 different types, and we'll discuss and explain those. And in the biological sense, I'm going to talk about 2 different ways of characterizing how biological systems achieve autonomy, constitutive and behavioral. The words on this slide that are important to write down at the bottom are homeostasis and allostasis. And I'll explain that in just a moment. And of course, this is just a preview, so we'll take much more time over it in the course itself. For those of you who studied control theory, you'll recognize this immediately as being a normal negative feedback loop. And that's effectively what homeostasis is, achieved through the chemical systems in a biological body. Now, when you add in prediction based on prior knowledge and based on sensing, you effectively have a system which is adjusting to the environment before things happen. And that is probably the second big take-home message from today, that that's effectively what cognitive systems do. They adjust before things go wrong. So they're always predicting. It's a prospective process. There's an interesting question which arises, which is what's the relationship between autonomy and cognition? And so here I've drawn effectively a Venn diagram which shows that they overlap. But like all emerging disciplines, not everybody agrees. So some famous people believe, in fact, that cognition is a subset of autonomy. Autonomy is a bigger family of computational models. I personally would adhere to that. So I think autonomy is something that is essential to characterize if you want to understand cognition. Okay, so have I overloaded you too much yet? Okay, hopefully not. So stay with it. We're about, I'd say, halfway through our webinar, and I'm going to carry on now and talk about another puzzle called embodiment. Now, the key thing here is that there are different types of characterizing embodiment. There are different ways that a system, a computer-based system or a biological system, can be embodied. And that gives rise to different types of cognition. Here we've got embodied cognition, situated, embedded, grounded, extended, and distributed cognition. If that sounds confusing, it is confusing. And so what we'll be doing in this course, we'll be spending a few hours discussing that so that by the time you're finished, you will be able to explain to me exactly what the differences are. And there are important differences to understand. But if I can characterize embodiment with this slide, the key definition then is the words in red. The point is that cognition is not just a brain-based activity. It isn't just the brain that's involved in cognition. It's actually the body as well. And I'll show you lots of examples of where the body influences or plays a role in how systems actually go about engaging in cognitive behavior, in predicting the future, and in acting effectively. Again, we're going to meet a common theme in this course, and that not everybody agrees. And in fact, there's a little bit of a standoff in the scientific community as to whether or not cognitive systems have to be embodied or not. And we'll have a look at that debate and see who's right and who's wrong, or where the line should be drawn. One of the things that we're going to talk about in embodied cognition is a thing called the conceptualization hypothesis. There are 2 others we'll talk about, but let me talk about this one just for a second. The idea here is that the way you are configured, what you look like, what your hands look like, whether or not you've got hands if you're a cognitive system, that shapes the way that you view the world. And that's very important if you want to build a system. It means that you have to pay attention to how you design the physical appearance and the physical capabilities just as much as you have to pay attention to the AI in the system. And this is a student of mine gave me this cartoon one time when I was trying to explain it. He said, this is what you mean. It means that based on your physical configuration, you see the world a particular way. And that's the way it is for you in everything you see. So you see the world as you are. the rhino sees it and sees nothing wrong with always having something conical in front of it in the middle of everything it sees. Okay, let's move on to learning and development. So learning and development sound like they're the same thing, but in fact they are slightly different. So I define learning as a process which estimates the parameter values that define a behavior in a model that's already known. Development is different. It's a harder process. It's the process of actually discovering or generating that model itself. So they are quite two different things. In machine learning, the course which you're going to take, some of you anyway, we're going to talk about 3 different types of learning: supervised, reinforcement, and unsupervised. And there's a very easy way of distinguishing between these. Supervised, you get directional error signals, vectors. With reinforcement learning, you only get scalar input, and with unsupervised, you get nothing at all, and it's up to you to cluster the data that you're learning from in order to come up with and recognize patterns in that. Turns out that the brain does this in 3 different parts of the brain: in the cerebellum, the basal ganglia, and the cerebral cortex. So talking about the brain, how about memory and prospection? Well, memory is, we all know what memory is. Memory is how you remember what happened. Well, in fact, there's a lot more to memory than that. We can distinguish between different types, short and long term, between declarative and procedural, semantic, and episodic. And I'll walk you through all of those. But what I'd like you to remember, the third thing I'd like you to remember from today, is that memory doesn't just work backwards. It's not about looking back. It's also about looking forwards. In fact, memory is there to allow you to predict what will happen. And we use that in cognitive systems in order to simulate the future. And by simulating the future, we can predict what will happen, and then we can prepare ourselves to act accordingly. And this is a picture of a simulation hypothesis taken from one of the experts in the field, German Tesla. So, with memory under our belts, we'll then move forward and we'll talk about knowledge, and we'll talk about representation. Again, something that you're going to learn about in the AI course. So the key thing here is, how can we acquire knowledge, and then how can we share knowledge with others? So we can program it in, and we can take that out. We have direct access in the cognitivist paradigm. And that allows us to use the internet. And today, a lot of work has been put into allowing robots to share their experiences over the internet. There are internets now dedicated just to robots, so robots connecting to each other over the internet and sharing experiences, knowledge, and know-how. It's a part of what's evolving to be the Internet of Things. Incidentally, this is something that you'll learn about in web technologies. And then finally, in acquiring and sharing knowledge, there are different ways that you can teach a robot or any system anything. But one of the ones that we like most is by allowing them to observe for themselves and then figure out how to do it for themselves. So we'll talk about the different ways that you can learn from demonstration. This takes us on to the final, the 9th part of the course, social cognition. And here we talk about not a single, so far all of the agents I've talked about, all the cognitive systems, have just been working on their own. Here we bring agents together. In this case, I've got a human being and a robot. And the idea is that we want, in social cognition, we want agents to help each other. So we would like them to be able to cooperate and to collaborate. And there are a number of issues here. In this particular case, the robot can see that the human's got an injured hand, and therefore, if he's thirsty or she's thirsty, that it should do something about it. So this, again, you can see involves predicting the future and inferring the intentions, figuring out what other agents want you to do. And you can see that's what we'd like our robots to be able to do. We'd like robots and cognitive systems, embodied or not, to be able to help us. And we'll talk about how we might go about building systems in the 9th part of the course. So that brings us the full circle. The nature of cognition then is all about how we think with our brains, but not just with our brains, how we think with our bodies, and then how we use those to interact effectively with others around us. We'll be using some books to provide us with some background reading. This is one that I published 3 years ago, but mostly we're going to be using a new book that's coming out next year published by MIT Press, which is effectively a summary of everything I've been talking about for the past 15 minutes or so. So we're done. That was a very quick and hopefully understandable tour through the course. So if you've got any questions, I'll be happy to answer them. And there you are. So I'll hand back and answer your questions.
Thanks a lot, Professor Vernon, for a very interesting and informative presentation. Guys, now it's time for your questions. So I'll explain the procedure again. If you have any questions, you should type them in the questions box, and I will read them to Professor Vernon, and he will answer all your questions. Okay, we'll wait for a few minutes. Well, okay, and Professor Vernon, we received the first question. So it's from Rinat Shaykhudinov, and he asks the following question. Will this presentation be available for downloading? Yeah, well, I think I can answer this question. Yes, Rinat, the recording of the webinar will be available on the internet. Actually, we're going to post it together with the answers to your questions. Yeah, you'll find it on YouTube. And there is another question from Dmitry Chesnakov. So, in the course you are referring to, for MOOC course, okay, are you referring to a MOOC course or a course at Innopolis? So, I think I can answer this question as well. So, we were talking about the course which will be taught at Innopolis University. So, thank you, Dmitry.
So just to add into that, the course title is Artificial Cognitive Systems, as you can see from the slide, and course code 421, so that means it'll be in the second semester of the coming academic year.
Any other questions? Mm-hmm. So we received another question. Okay, Professor Vernon, it's from Anatoly Sviridenkov. Sorry, I'm not sure if I'm pronouncing the name correctly. And the question is, what do you think about deep learning for cognitive? Is it possible to combine symbolic and sub-symbolic levels?
Yeah, it's a great question. A very, very large part of the community thinks that is essential. Remember when I talked about cognitive architectures, I talked about very, very briefly, I mentioned the cognitivist and I mentioned the emergent. The combination of the two, trying to get the best out of both, is called a hybrid cognitive architecture. And there are a number of very famous cognitive architectures which are hybrid. The most famous is Akhtar, Clarion is another one, and Isaac. And the key idea there is exactly to do as what you're suggesting, is to combine the symbolic with the sub-symbolic. So symbolic effectively means knowledge which is explicit and represented with symbol systems, and then sub-symbolic means knowledge that is represented implicitly through, for example, neural networks. So that's how hybrid systems work. They combine both. But I should say, though, that not everyone believes that that is how cognitive systems actually work. So those who come from the dynamical systems community argue that, in fact, symbol systems are inventions of cognitive systems to assist them in an external way accomplish tasks, but it's not actually how the brain works. So this is a very, very old debate between what we call the good old-fashioned AI people and the nouveau AI people working in neural networks. So connectionism. So great question. The answer is there's no definitive answer, yes or no, but a large part of the community around the world is trying to do exactly that, to combine both. So I hope that answers your question.
Thanks a lot, Professor Vernon. Okay, thank you for a very interesting question, and you may keep sending your questions to us both in Russian and in English. Okay, we received another question from, it's Renat Shaykhudinov again. And the question is, how do you test these complicated behaviors? I mean, it's simple to test a simple function by writing a unit test.
Yeah. Hey, another good question. Yeah, so unit testing effectively, given a particular component, how well does it work? And you can do your verification, your validation, and you can evaluate how well it works. But if you've got a very complicated system, how can you test it against something when you're designing it to deal with what's not predictable? So you really have a puzzle on your hands here. So there's two parts to the answer. The first part of the answer is that nobody's actually built a complete satisfactory cognitive system. The most advanced ones come from the AI field, the cognitivist ones like SOAR, and the least advanced and the least mature come from the emergent systems, the dynamical systems, and the neural networks. But benchmarking and assessing how well they work is a difficult problem, because effectively you've got to come up with a test where you're injecting noise and uncertainty into it and then seeing how it deals with that. In most scenarios, in most research labs, in most places around the world, they actually just take your system and they use it in, for example, in domestic circumstances. So there are scenarios where they try and help. In one lab in Bremen in Germany, they get the robot to make pancakes or to cook sausages. In the United States, their test bench is based on trying to get a cognitive robot to drive a car and enter a building, climb a ladder. And there are student competitions around the world which are focused on, for example, search and rescue, and in trying to get robots to deal with uncertainty that's been put in their intention. So it's a tough thing to do, but it's one of the problems is that we really don't have systems which are capable, which are as resilient and as robust as we'd like them to be. As our systems get more sophisticated, it's going to be a bigger problem.
Thanks a lot.
It's a good question. Sorry, I'll just add. It's something that I haven't addressed in the webinar, and it's something that I think I might say more about in the course, is benchmarking and evaluation scenarios for cognitive systems. Good question.
Thanks a lot, Professor Vernon, and we received two more questions. So one of the questions is, from which area do you expect breakthroughs? So there are three areas mentioned here. It's brain simulation or brain modeling, machine learning, and classical strong artificial intelligence.
Oh, I'm going for machine learning on that. I think, I mean, there are three very complementary and very important areas. In the brain modeling, there's a massive amount of research work going on in trying to effectively understand how the brain works. And we draw a lot of inspiration from that. So I'm not discounting that that's going to be very, very important. In fact, I don't think we're going to make a great deal of progress without learning from how the brain and the body together, because it's a complete system. The brain is part of the brain-body system. Works, so it's not enough just to model the brain, but also the central nervous system. The third area, which was in conventional knowledge-based systems, there's a limit to the amount of advances I think we can leverage from that. So for me, I think the early breakthroughs will come through advances in machine learning, and there already have been big advances in learning today. Anyone who uses any search engine or online shopping system is dealing with a system that's learning from your every interaction and learning how to profile you and your preferences. So there's a lot of good stuff we understand there. And the three types of learning that I mentioned, the reinforcement, the supervised, and especially I think the unsupervised. The unsupervised learning where you can figure out where there are patterns and what the patterns are in unstructured data. And you get that in many other areas, not just cognitive systems, but in data science as well. So that's where I think the early benefits and the early breakthroughs will come. And I think that the next thing after that will be leveraging a better understanding of how human and animal cognitive systems develop. And I mentioned the word development specifically because development is the next level up from learning. Learning, if you will, is figuring out the parameters of a model, and then development, well, trying to figure out, well, what's the model in the first place. And that's we need to learn, or we need to get inspiration from something, and the only proof of cognition that we have at the moment is our human systems and some animal systems. So that said, I don't want to give you the impression that I think knowledge-based systems aren't any use. In fact, today they are the ones that work best. So I'm a big believer in carrying on research and trying to leverage more out of that. Whether or not it'll yield massive breakthroughs is a different question.
Thanks a lot, Professor Vernon. The next question is from Viktor Smirnov. He asks, Professor Vernon, you mentioned you distinguish learning and development conceptually. How common is this distinction in the cognitive science and/or robotics?
It's a nice question. I have to say that's a distinction that I've invented and published, mainly because if you read the literature, there's a lot of confusion between it. But I've been using that for a number of years, and people, it seems to make sense to a lot of people. But I'm not going to put my hand up and say that all the world agrees that that's the correct distinction between them. But one of the issues, the problems, is that development is a term that's been borrowed from the soft sciences, psychology, and neuroscience. And it's not one that was produced by the machine learning community. So you could also imagine that a learning system could learn a model in the first place, and of course then, according to my definition, that's development, and you've got your confusion back. But as a first order way of distinguishing the two, it's very, very helpful to distinguish between how do you identify parameters, how do you learn parameters, and how do you identify then the actual model of which those are parameters. And those are two quite different things.
Thanks a lot, Professor Vernon.
Was there a second part of that question that I've forgotten?
No, that's it. The question was how common is this distinction in the cognitive science and robotics? Yeah. So if you have anything to say about robotics.
That's it. About robotics, well, the only thing I will mention about robotics is that there is a branch of robotics called developmental robotics. And it's focusing mainly on learning and, to a lesser extent, growth. When you talk about development, it's very important to remember that development there's a second half of development which is to do with growth. And if I get a chance in this course, I will actually introduce you to some mathematical characterizations of growth and development in terms of information theory, which was derived from some work done by people in computational ecology several years ago. But the difficulty we have in robotics today is that we build our robots out of metal, and we build them out of fixed materials, and they don't have the ability to grow. So it poses the robotics community with a bit of a conundrum. So the best that they can do is try and develop an understanding of the world. And there's a particular branch of cognitive science which is called enaction. It's on the emergent side, and it is characterized by exploring the world and making sense of the world around you in order to maintain the autonomy of your the system's own autonomy. But that idea of making sense of something is all to do with trying to build a model, what works and what doesn't, and throw away the models that don't work and keep the ones that do, and then refine them and improve them. So to a very large extent, that type of sense making is what we would characterize as development. And I'll also say that development is characterized by two fundamental changes in the system, which is not necessarily the same as learning. So when systems develop, two things happen. One is that the actions in which they can engage extend, so that they've got more and more things that they can do, so the repertoire of actions increases. And the second thing that happens in development is that the timeline of your prospective, your predictive capabilities extends into the future. So initially when what we call altricial species, which require development before they become independent, initially they deal with things that happen in the world with a very short timeline, seconds and minutes. And as they develop, because they're building better models with greater predictive capability, they have greater prospection, a greater ability to see what's going to happen now, not in 5 minutes, not in 10 minutes, but in 20 minutes, in an hour. And that's exactly what we as humans do. We imagine how things will play out in minutes, hours, days, and weeks. And that's a product of your developmental process. That wouldn't necessarily be a characteristic of a learning system.
Professor Vernon, thank you very much for such a detailed answer. And we received another question. So, in your presentation, in your graphs, you pay a lot of attention to different types of memory. Could you explain why do we need so many types of memory? Why does the machine need so many types of memory?
Mm-hmm. Okay, that's a nice question. And the answer is actually fairly straightforward. There are two, if I can say, two types of I'll say information. There's knowledge, that is effectively facts about the world. So the thing that metals are hard and some birds are white, and that boiling water is very hot and you need to be careful. So we call that declarative memory. The other type of knowledge that we have is called know-how. So this is our skill-based knowledge. It's our ability to do things. It's to do with our actions. And that's a separate type of memory, and it requires different representations if you're building an artificial system. We call that procedural memory. But also, memory has a limited lifetime. So we forget. We'll spend a little bit of time about the process of forgetting and so on. In fact, it turns out to be quite important to be able to forget. And so we've got short-term memory and we've got long-term memory. You can distinguish it in that way as well. In terms of if we talk about facts, we can view knowledge at different levels of abstraction. We can view knowledge as just something that is, well, I would say, close to your sensory understanding of something. When you smell a particular smell, like bread or coffee, that allows you to associate memories very, very readily with those. But that's not something that you particularly reason about, or that you engage in some kind of rational process. We call that episodic memory, memory that is actually eidetic. It's there, and it's very easily associated with other types of memories. But that's quite different from abstract knowledge, which I could call symbolic, but I don't particularly want to, because that would require you to adopt a particular approach. But you know, for example, mathematical knowledge would fall into the second category. We know things about circles and the properties of certain curves. We know about force, we know about dynamics. This is all, I'll use the word conceptual knowledge. It's still declarative knowledge, it's factual knowledge, but it's not the same thing as the sensory episodic knowledge. So as you begin to understand the different types of knowledge that you need in order to function well, you realize that you need different types of memory and different types of representation. Now, don't get the idea that your brain is nicely compartmentalized. It's got that type of procedural memory over here, and that type of declarative over here. These are distinctions which we impose in order to help us understand and characterize the system. But they're useful characterizations. And all modern cognitive architectures now make these distinctions. And they're the things that we want to talk about in the course.
Thanks a lot. And we received another question. So, how important is the phenomenal consciousness modeling problem in temporary cognitive systems?
Consciousness. I'm very proud of the fact that I didn't mention consciousness, because we find it very difficult to understand the processes by which we build cognitive systems. And consciousness takes it to a whole new level. That said, some people, some very important people, believe that understanding consciousness is an integral part of it, and there are computational computational consciousness conferences and journals. And how important is it? It depends who you ask. My own personal feeling is that it's a subject which is not necessary to understand cognition. It's very desirable, and it's something I think that could come later. But it will require a very deep understanding of how language influences cognition. And some of you out there may have noticed I've said very, very little about language. It's a whole area all on its own. And I won't be saying much about it. But apart from one thing, is that language is very deeply involved in the emergence of consciousness in cognitive systems. But consciousness is not something I'll be saying anything about.
Thanks a lot, Professor Vernon. The next question will be about logic. So, and the question is from Anatoly Sviridenkov again, very active attendee. So, do you use any particular logic for knowledge? If yes, what type? Is it first order logic?
Yeah, a number of logics are used. I personally haven't used logic greatly because most of my work has been in the emergent side. But yes, all of the production systems that we'll talk about in SOAR use logic, and it's basically predicate logic.
Thanks a lot, Professor Vernon. Yeah, I'm afraid that's all the time we have. So, okay. Yeah, but guys, if you have any more questions, yeah, just send us to them. Just 1 or 2 questions, because our time is up. If not, then I would like to remind you that the course in artificial cognitive systems will be taught at Innopolis University. So if you want to learn more, join Innopolis University. And we will also select the author of the best question tomorrow, and the winner will be notified by email. So, and I would also like to remind you of our next webinar, which will take place on February 25th, and the webinar will be dedicated to component-based software engineering. So we encourage you to join this webinar too, because it's going to be very interesting and very informative. So, yeah, if you still have any questions, you may send us an email to webinar@innopolis.edu.ru, and Professor Vernon will answer them later. I see there are no more questions. So I would like to thank you all for joining this webinar. I hope you liked it. Well, I personally totally loved it. It was very interesting, very informative. And, well, I wish you a good rest of the day. Join our webinars again. So, goodbye, everyone. And Professor Vernon, thank you very much for your presentation, for your answers. We appreciate it. You did a very good job.
It was a pleasure, and I hope the participants enjoyed it and got something out of it. And if you have more questions, I'm always here to answer them. Okay. Thanks for your attention.
Thanks a lot. Goodbye.